Hey everyone, welcome to this explainer. Imagine looking at a completely flat piece of paper and suddenly, boom, a rugged, towering mountain range just rises up right in front of your eyes. Maps, well, they aren't just flat drawings. They're actually a secret two-dimensional cipher that's hiding a rich three-dimensional world. And today, we're going to crack that code together. Okay, let's dive right into this. Here's our agenda, basically our navigational legend for the journey ahead. We'll hit 1. Mapping the third dimension. 2. Cracking the contour code. 3. Identifying landforms from lines. 4. Reading rivers and valleys. And finally, 5. The secret language of map. Let's kick things off with Section 1, Mapping the Third Dimension, the Cartographer's Dilemma. So I want you to really put yourself in the shoes of an early mapmaker for a second. You've just explored this massive, dynamic landscape, and now you have to share its true layout with the world. But you're facing a nearly impossible task. How in the world do you fit a 3D mountain with its length, its breadth, and its towering height onto a perfectly flat piece of paper? The Earth's relief features are beautifully three-dimensional, but your canvas only has 2. Well, early cartographers tried a few kind of clunky methods to solve this. First, they tried something called hatchers. These are short, disconnected lines drawn in the exact direction that water would flow down a slope. But honestly, they're incredibly tedious to draw, they're super hard to interpret, and the biggest problem, they don't actually tell you how high the land is above sea level. Then there was hill shading. This acts like a giant imaginary lamp shining on a relief model to create light and shadow. And sure, while it gives a really neat 3D illusion, it actually obscures important topographical details and, again, gives you absolutely zero accurate height data. Mapmakers desperately needed something vastly better. Which brings us to Section 2. Cracking the contour code, the master key. This right here is the ultimate solution for accurate map reading. Consider this your primary decoder ring. The absolute baseline rule you need to know is this. Contour lines are imaginary lines joining places which have the exact same height above mean sea level. Think about it. If you were to walk along a single contour line drawn out on the Earth, you would never go uphill and you'd never go downhill. You'd stay perfectly level the entire time. And on our maps, these absolute lifesavers are usually drawn in brown. Now, what's really interesting is how these lines are spaced vertically. The vertical distance between any two consecutive contour lines is called the contour interval. If you look at the spacing here, you'll spot a thick contour line sitting at 300 meters, and then the very next thin one is at 320 meters. That means the contour interval is exactly 20 meters. And the beauty of this is that this interval stays completely constant across the entire map, giving you a perfectly scaled understanding of the elevation. But wait, how steep is the actual climb between those lines? Well, we calculate the gradient by walking through 3 really simple steps. First, find that vertical interval, or VI. That's the height difference we just talked about. Second, measure the flat horizontal distance on the map between your 2 points. We call that the horizontal equivalent, or HE. Finally, just divide the VI by the HE. So what does this all mean? If your math gives you a ratio of 1 to 5, that means for every 5 units you walk forward, you climb 1 unit straight up. That is a seriously steep, exhausting climb. But a ratio of 1 to 50? Well, that's just a nice, gentle stroll. All right, moving on to Section 3. Identifying landforms from lines, seeing the shapes. It's time to shift away from the basic math and start visualizing real 3D geographic features just popping off the page. Look at the tightly packed contour lines on the left side. When the land suddenly drops or rises, the lines are totally squished together, which instantly tells you you're looking at a steep slope or a cliff. Now, on the right side, the lines are widely spaced apart. This gradual change in elevation means you've got a gentle slope. So just remember the golden rule. Tightly packed equals steep, widely spaced equals gentle. Let's build on that. Look closely at this pattern. When you see almost perfectly circular contour lines, and the values are decreasing as you move outward, you're looking at a conical hill. It has a high summit directly in the center and slopes evenly down on all sides to a broad base. It's quite literally like looking straight down at a perfectly symmetrical traffic cone from above. Of course, real landscapes get a whole lot messier than traffic cones. Here we're looking at elongated features. A water divide, or ridge, acts as a long, narrow highland that separates rivers or tributaries. Take a look at the water divide in this diagram. On one side of the ridge, the contours might be drawn really closely together, creating a steep slope. That's called a scarp. On the other side, they're drawn far apart, creating a gentle dip. Recognizing these asymmetric shapes is absolutely crucial for predicting the terrain you're about to hike into. Next up is Section 4, Reading Rivers and Valleys, the Flow of Water. Let's decode exactly how water interacts with this landscape. There's a vital rule you have to remember here. When contour lines cross a stream or a valley, they form a V shape pointing upstream, meaning they point towards the higher elevation. And interestingly, water carves a literal timeline right into the map. A river's life has 3 very distinct stages, which are clearly visible in these cross profiles. In the upper course, you get steep slopes and narrow V-shaped valleys because fast water is violently cutting into the rock. As it flows down into the middle course, the gradient lessens. That creates gentle slopes, broader floodplains, and those classic meandering curves. Finally, in the lower course, the land is nearly flat, and the tired river just lazily spreads out into deltas before it finally hits the sea. As these rivers flow over thousands of years, they carve specific, highly readable, visual patterns right into the earth, based entirely on the underlying rocks and gradients. We call these drainage patterns. Let's do a quick rundown of what each pattern signifies to a hiker or an explorer. Dendritic patterns, they look like the branching veins of a leaf or a tree, and you'll typically find them on flat, uniform lands. Trellis patterns look a lot like rectangular grids with streams joining at right angles. That actually hints at alternating bands of hard and soft rock down below. Radial patterns spread outward from a central point, kind of like spokes on a bike wheel. That is a massive visual clue that there's a conical hill or a volcano right in the middle. And finally, disappearing streams are shown by broken lines. They're a warning that the stream doesn't reach another river or the sea. It simply dries up into porous sand or drops completely underground. Pretty cool, right? And finally, Section 5, the secret language of maps, bringing it all together. This is the phase where we synthesize all these decoding skills we've just learned. Before you even read a single contour line, the map's universal color key instantly reveals land use and passability. It's like a cheat code. Black is used for names, latitudes, and railways. Blue, no surprise here, always means water features, like perennial rivers or wells. Green indicates forests and orchards, while white warns you of rocky, uncultivated badlands. Yellow shines brightly to show cultivated farmlands. Brown, as we've spent a lot of time discussing, is reserved for our trusty contour lines and sand features. And red, that's the color of human infrastructure, roads, cart tracks, buildings, and the map's grid lines. Let's see how this all builds into a real topographical sheet. Look at how these elements interact perfectly on the page here. You can trace the brown contour lines weaving around the hills, easily noting exactly where they bunch up for a steep, treacherous drop. You instantly spot the red grid lines and major highways slicing right through the yellow cultivated fields. You see the white patches of broken rocky ground and the blue perennial wells scattered around. Suddenly, this isn't just a flat piece of paper with chaotic lines anymore. It's a thriving, three-dimensional world that you can now mentally walk through before you ever step foot outside. We live in a world of GPS and digital turn-by-turn directions, but I really want to leave you with this powerful, provocative thought straight from our source material. But when one enters places such as the wilderness or the deep seas, cell phones lose connectivity and map reading becomes a key survival skill. Understanding the secret language of these topographic maps isn't just some fun academic exercise. It's a vital tool for empowerment. Think about it. When the glowing screens go dark and the digital world fails, do you have the knowledge to navigate the real one? Thank you so much for exploring with me today. Keep decoding the world around you.